equation for delta S of the surroundings is negative delta H over T. And again, T must be in Kelvin. So I'll do A, and then y'all can do B and C. There's no tricks. You just plug in your delta H of negative 2045 kilojoules, and you plug in your temperature, but your temperature has to be in Kelvin. Okay, so when we calculate delta S here, we'll have 2045 divided by 298, and that gives us 6.86. Our units for this are kilojoules per Kelvin. Okay? Go ahead and do B and C, please. Good. 1.06 kilojoules per Kelvin is what I got for letter B. And what'd you get for letter C, Chris Drake?
I got 0.148 kilojoules per Kelvin.
It should be negative.
Oh, right.
Delta H is positive, so this should be negative, right? Make sure you have the signs and the units are very important in these two chapters. Okay, if you look at the next sample problem, it's a little different. It says, determine if the values of entropy in each of the following will produce a spontaneous process. Also, which of the following processes is endothermic from the perspective of the system? So, let me tell you what to look for. There are at least two ways to tell if a process is spontaneous. You're going to learn the second way in just a minute. The first way we know, or what we know so far for a process being spontaneous, is that delta S of the universe must be positive. Okay? If delta S of the universe is positive, the process is spontaneous. Again, we will learn another way to calculate or to determine if a process is spontaneous in just a minute. Okay? So, also recall from yesterday that we learned an equation for delta S of the universe. Whoops. And delta S of the universe is equal to delta S of the system plus delta S of the surroundings. So you should be able to go ahead and calculate that to see if delta S will do it for A, what delta S of the universe is. So if I do it for A, and then you can do the rest, we'll kind of do A together. Delta S of the system is 30 joules per Kelvin, and delta S of the surroundings is 50 joules per Kelvin. So delta S of the universe will be 80 joules per Kelvin. So yes, A is since it's positive, A is spontaneous. Yeah, you just add them. Okay? So since delta S of the universe is positive, process is spontaneous. But there's another part of this question. They want to know if the process is endothermic. And it's kind of confusing when it says from the perspective of the system, because it makes you think like you need to look at delta S of the system. You are not. If the system undergoes an endothermic change, where does it get that energy from? The surroundings. So what should happen to the entropy of the surroundings if the system undergoes an endothermic change? It should go down, right? It should be negative. Okay? So if a process is endothermic, then the heat comes from surroundings. And delta S of the surroundings will be negative. So it's tricky because even though they say from the perspective of the system, you don't really, to tell if it's endo or exo, you don't look at delta S of the system. You look at delta S of the surroundings. And if it's positive, that means their entropy went up. The reason their entropy went up is because they absorbed heat from the system. So the system this one would be exothermic, not endothermic. Okay, you need a negative delta H in order to be endothermic for delta S of the surroundings. You can see how this gets confusing, okay? All right, go ahead and finish B, C, and D right now. Is B spontaneous?
Yes.
Yes, because delta S of the universe would be positive. Is it endo or exo? It's exo because delta S of the surroundings is positive. So it's spontaneous and exothermic. Jess Wilson, letter C. Is it spontaneous?
Yes.
Yes, it's spontaneous because you add them together and it's positive. Is it endo or exo, Tori? It has a negative.
Oh wait, no, that's endo.
Yeah. It's endothermic. Okay? It absorbs heat from the surroundings, which makes the entropy of the surroundings go down. So that's how we know. So if it's a negative delta S, it's endo. Okay? And then finally, Sarah Wilson. Sarah Wright. Letter D, is it spontaneous?
No.
Not spontaneous. Because when you add these together, it's negative. Endo or exo? Endo. Okay? Again, I get it confused in my head, so I know you're going to get it confused in your head. What you're looking for, if it's spontaneous, delta S of the universe has to be positive. If it's endo, to determine if it's endo or exo, you look at delta S of the surroundings. If the surroundings are positive, the system is releasing heat, exothermic, delta H would be negative. Okay? Delta S of the surroundings would be positive. Delta H of the system would be negative. Okay? It's exothermic. If the entropy of the surroundings goes down, then delta S of the surroundings is negative. It's losing heat. Heat is being absorbed by the system. The system is endothermic. Delta H is positive of the system. Okay? So I think it's important that maybe we make a note of this because it is kind of crazy. Right? So if it's spontaneous, delta S of the uni is positive. If it's not spontaneous, delta S of the uni is negative. Okay? If the reaction, I'm just going to say reaction is the system, is endo, delta H is positive, but delta S of the surroundings, God bless you, are negative. Did I say God bless you? Okay. If the
You just said it.
God bless you again. If the reaction is, it just becomes second nature. It's kind of like when you're driving to work and you don't even know how you got to where you are. You're like, wow, I don't even remember getting on that throughway.
That's how I feel like when I come to your room every day.
Because you're always here.
I know.
So if the reaction's exo, delta H is negative, but delta S of the surroundings is positive. Okay? That may be helpful to have it there. Because I can't keep it straight in my head. I have to really focus when I'm telling you that.
Alright, so what's the zone
We good there?
is? Yeah. So what's the zone?
Jess is still writing. Pinky's still writing. Don't rush him. Okay. This is really important, this next little thing, and I'll tell you the next section. And then maybe I'll tell you another story. We did get the chirper last night. The chirper was sacrificed last night. Oh no, there was another chirper that we got. Yeah. Eric was laying in bed the night before. We bought crickets, and it was real quiet. And then all of a sudden, after about 15 minutes, he's like, "Oh no!" I'm like, "What? What's wrong, buddy?" He's like, "We got a chirper." I was like, "Oh no!" It was funny, but he got him last night, so we had a nice night last night. Sacrifice the chirper to the lizard. Okay, there is another way. I told you this was coming. There is another way we can calculate whether or not, or determine whether or not a reaction is spontaneous. And that's really what this is used for. And that is this thing called Gibbs free energy. Okay? It is, we can calculate the change in Gibbs free energy, and the equation for it is delta G degree, meaning we use these values when we're at standard state, 1 atmosphere of pressure, etc., equals delta H degree, that's our enthalpy, our heat of reaction, which we have many ways to calculate, right? Hess's law, calorimetry, heats of formation, minus T delta S degree. I did say S.
I mean X.
Oh.
So I wrote X.
So delta G degree is your Gibbs free energy. It's really hard to define, and it cannot be measured. So there's no tool or device that can measure the free energy. It can only be calculated, the free energy of a system. It can only be calculated in more than one way, but this is one way we can calculate it, okay? The units for Gibbs free energy are going to be in kilojoules or joules. It's your choice per mole. Okay? The delta H degree, as you know, is our enthalpy. Kids get confused between entropy and enthalpy. Enthalpy has an H in it. Entropy doesn't. Okay, so the one with the H in it is the delta H. Enthalpy is your, and the H stands for heat. Right? And that will always be given in kilojoules per mole. The T is your temperature, and that must be in Kelvin. It must be. It's not like you have a choice. And the delta S degree is your entropy. And unfortunately, they will give it to you in joules per Kelvin. So they're going to give you the delta H in kilojoules and the delta S in joules. And so you're going to have to convert one. And it makes sense to convert your delta S. So I'm just going to tell you, you must convert your delta S to kilojoules per Kelvin. Okay? You must do that before you can plug anything into your equation. Because you cannot subtract something in kilojoules minus something in joules. They have to be in the same unit. Now, if delta H, and again, I'm skipping over a lot of the theory. I want you to read it. They walk you through all the why it is so in the book. But if delta H is negative, delta G. If delta G is negative, okay, then the process is spontaneous. If delta H is positive, then the process is not spontaneous. Okay? So now we have another way. And this is a more tested way of how you can predict if a reaction is spontaneous or not. So really, everybody, there are 4 scenarios that you can have. Okay? Okay, remember, if delta H is positive, if you've forgotten, the reaction's endo. If delta H is negative, the reaction's exo. If delta S is positive, that means the entropy of the system increases. This is all with respect to the system. And if delta S is negative, the entropy of the system decreases. Okay? If you remember when we started chapter 16, I told you spontaneous processes will happen for one of 2 reasons. Or the 2 driving forces for a spontaneous process are A, to lower the energy. So the process would be exothermic, right? Or B, to increase the entropy, correct? So if both of those values are true, if delta H is negative, right? If we have a negative delta H and we have a positive delta S, figure this out with the equation. If this is negative, right, minus T, and this is positive, agreed? You're okay? Then the only sign delta G can have is negative. So if the reaction is exothermic and entropy goes up, then in all cases, at all temperatures, let's say that, in all cases, at all temperatures, delta G is negative, and the reaction is spontaneous. So when both of your factors are true, right, what you need to be spontaneous is either exothermic or increasing entropy. If both of those are true, you are always spontaneous. Temperature is insignificant. You're always spontaneous. Temperature will just determine the magnitude of delta G.
Isn't that why it's always a temperature controlled, so you can't really negative?
Correct, correct. However, if only one of these, well, let's do neither. Let's do the bottom one. If the reaction's endothermic, if delta H is positive, okay, and delta S is negative. So if we are absorbing heat and our entropy is going down, we don't have either factor met, right? We need to be exothermic or increase our entropy to be spontaneous, to have a negative delta G. Okay? So if we're endothermic and our delta H is positive, and our entropy is decreasing, so our delta S is negative, then what's the sign of delta G? Positive. Does temperature matter? No. Delta G can only be positive. And what that means is that the reaction is never spontaneous at any temperature. Ever. But what if only one of the factors is true? Okay? They love essay questions about this on that AP exam, guys. First you'll be calculating like delta H and delta S, and then they'll be like, or maybe not. Maybe you won't even calculate them. They'll just say, is the reaction spontaneous as written? And then you have to put these, you have to really think about the table. I just use the equation, okay? So let's say that delta H is positive, so we're endo. They'll give you the delta H, say, and delta S is positive, which you can tell if delta S is positive just by looking at the reaction, right? If you're making more gas, then entropy's going up. Delta S is positive. So let's say delta S is positive, okay? Well then, depending on which of these numbers is bigger, kind of think of these like two different factors here. That's how I like to think of these, kind of like two different factors. The delta H is positive, and then this expression would be negative, right? Because a negative times a positive is a negative. So depending on really the value of T, this could be negative. The overall delta G could be negative. So if this expression, when you multiply it, is bigger than this number, then delta G will be negative. So what we would say then is that this situation would be spontaneous at high temperatures. And again, spontaneous means have a negative delta G. Because as temperature goes up, this is the language that they use. As temperature goes, they don't say as temperature goes up, what is the word? Driving force is the word they use. Entropy becomes the driving force for the spontaneity of delta G. But at low temperatures, this is a bigger number than this. So when T is low, then delta H is the driving force for the lack of spontaneity for this reaction. So if the positive is a bigger number, then delta G will be positive. If this is a bigger number, then delta G will be negative. And the way that this becomes a bigger number is by increasing the temperature. Okay? Now the other situation. What if delta S is negative, so the entropy goes down, but we release heat, right? Delta H is exothermic. We release heat. So this time, this is negative, and delta S is going down. This is negative, right? But a negative times a negative is a positive. So this time, the delta H side's negative, and the T delta S side's positive. Well, at low temperatures, delta H will be bigger, and the driving force for delta G. It'll have the most say in what the sign of delta G is. So this will be a bigger negative number than this is a smaller positive number at low temperatures. So at low temperatures, delta H is the driving force, and delta G will be negative and spontaneous in this situation. However, at high temperatures, then this side dominates. This becomes the driving force as the temperature increases. And this time, this side is positive. So if this becomes the driving force as temp goes up, and this is positive, then delta G will be positive and non-spontaneous at high temperatures. Yay? I think there's one practice question we did not do. Did we skip it?
Yeah,
Really?
There's one afterwards.
we're on top of it, Joe.
There's one about boiling point, isn't there?
Five and what is the real point?
Okay. Oh, well, you know what? I don't want to do those now. I want to let you kind of forget this a little bit and then come back on Monday and talk more about it. So I think we'll call it a day today. Homework number 4 is due on Monday. If you didn't get my email, I extended the deadline for the lab, so the lab is not due today.